Testing. Okay. This one.
So this is Sdnrg. We're going to just give it a few minutes and let people who are still on break wander in while we figure out how to use the AV.
Testing. Oh, here we go. Okay. I need to buy some new glasses for Dave.
Okay. So the blue sheets should be circulating. I don't know where they are. Whoever has it right now. Okay, there's a couple. So sign the blue sheets. I'll remind you as we keep going here. So as you might imagine, you're in Sdnrg, and if that isn't your destination, get off the plane now, or stay. Either way. We wanted to bring to your attention that a good friend of ours and member of the IETF community, Ping Pang, passed away recently, and we just wanted to put a picture up there of him. I don't know how many of you knew him, but he was a great guy, good friend, wonderful to work with, great IETF contributor. So we're all a little bit sad, but we just wanted to kind of dedicate this to him. So that's what that's about. And with that, I think we'll just dive in here. By the way, if anybody wants to make a comment on anything we're doing here, please do that. But when you get up, remember to state your name and affiliation if you can for the people who are taking notes. Okay, so IRTF IPR policy. I'm sure you can all read that, or you've all studied this in detail so you could recite it verbatim. But anyway, we were following the IETF IPR rules, so keep that in mind. And they're summarized here. If you don't know them, just look for the IETF IPR rules. So a little bit of administrivia here. There's a picture there, or there's a URL of where the Charter and Wiki is. It shows you where the mailing list is, where the proceedings are. Jabber, we don't have a Jabber scribe. Who would like to volunteer to do that? And if the answer to that is yes, raise your hand. That's how you'll tell us. Not everybody all at once. Hey, I got in trouble last time for not having a Jabber scribe. Somebody help me out here. All right. Well, if we can't get one, we can't get one. We have John Hudson giving us the regular scribe duty. So thank you, John. And the last thing is we need somebody to take minutes. Well, we're not having much luck with the audience participation section of our agenda here. Somebody needs to take minutes. Otherwise, we won't be able to run the group without that.
This is an interview opportunity as well to be the research group secretary, which we're also looking for. So think of this as a trial run. And we're here to help as well, so we don't expect you to sort of transcribe the entire session. Basically take the salient points and then we can review them post the research group session and update and polish and post to the list. So don't be afraid.
Again, not all at once. Oh, thank you very much. Thank you. You know, I felt like I had to do like United. $400, $500. Okay, so I think we got most of that covered then. Here's our agenda for today. The agenda bashing is about whether or not anybody has anything they want to add or subtract from this. This is what we're up to. I guess the one talk, the hyperelastic cloud talk, was postponed until next time. Okay.
Okay, Alberto, you're up.
Well, we just dive into it then, huh? Alberto. No.
Okay, so I'm Alberto Rodriguez. I'm with the Technical University of Catalonia, and I'm going to present you today research that we are doing on SDN architectures for end-nodes, particularly for home routers and mobile devices. Besides the architecture itself, I want to take advantage of this opportunity to raise some awareness of this scenario and to see if people think that this is a relevant scenario and think that some work should be done there. So. Shall you move the slides or myself?
Yeah, there should be a presentation mode. Okay, try that.
Okay,
Yeah.
now?
Oh, yeah.
Okay.
F11.
So, if you think of traditional SDN, you think of deployments on data center networkings, on one networks, on campus networks, these kind of things, but usually end nodes are always out of the picture. So what we want to do with this research is to bring SDN end-to-end, so from the data center to your phone. If you think of this scenario, you realize that you can't control everything on the network because you can't have control of the transit network that is there, the internet that is deployed already. But you can control a few things. You can control where the traffic is coming from your source, where this traffic is addressed up. If you are able to deploy some nodes on the transit network that is out of your control, but these nodes can be, you can control the path to some extent. Of course, for this, you need an architecture that is optimized for the scenario. The motivation to do this is that we think that this is a new and unexplored scenario. Although there are some works on the literature about SDN for nodes, those works just focus on how to enable SDN on nodes, but they don't cover the whole scenario. They don't cover a whole deployment of multiple nodes that they have to communicate with each other and to third parties. So this is what we are trying to address here. This scenario has a new set of challenges that are not present on traditional SDN that we have analyzed, that we have tried to cover and describe. And from those challenges, we have moved on into some design principles, design guidelines to overcome those challenges and be able to effectively deploy an SDN architecture for this scenario. So before going into the challenge and the design principles, I want you to think about some potential use cases for this scenario. So if we think about controlling the source, what you can think of is, for instance, a smartphone where you can dynamically offload traffic from the 3G interface to the Wi-Fi, or aggregate both interfaces to have higher throughput. If you think of controlling the destination, you can think of a specialized CDN that that redirect traffic to one CDN node or another, depending on the user that is trying to reach the CDN. Also, you think of controlling the path. You can think of a cloud service company that, by means of deploying these nodes on transit networks, they can redirect traffic to those nodes and offer rich in-path services. So this one, along with the next slide, I think that they are the most important ones on this presentation, because they present first the challenge and then the design guidelines. So this is the thing that we have seen in the scenario that may or not be present on other SDN scenarios, but at least for end nodes are quite critical and require new approaches to deal with them. So first of all, we are here dealing with a large number of controllers, in order of hundreds of thousands or even more. And although this is not this not only appears in this scenario, because SDN can nowadays, traditional SDN can deal with a huge number of controllers, this challenge combined with the rest of the challenge that I'm going to present makes this especially hard for a SDN controller to manage. So another thing is that end nodes usually are scattered over the network. Even in a worldwide deployment, and other SDN scenarios can deal with worldwide topologies. But the thing is that usually those traditional SDN deployments, the nodes are located in a few locations. And in an end node scenario, those end nodes are in multiple different locations. If you think of a common SDN switch, that switch is aggregating traffic for different end hosts and sources. But in an end node, the traffic it came from the end node itself. So there is no aggregation there, and each end node has to populate its own cache, its own tables, in order to be able to route the traffic properly. And also, and as you can imagine, if we are dealing with smartphones, with home router and so on, the network that we have in the middle is the internet, and you can't control the internet. So you have to deal with the internet and with the access networks that connect the nodes. Also, another thing that end nodes have that common SDN hardware doesn't is that they are transient devices. You never know when a node will be available. You never know when a new smartphone will show up. You don't know when a user will decide to plug his home router. So you can't count that the node will be there waiting for your policies. So based on these challenges, what we have done is to propose a series of design guidelines to overcome these issues. So first of all, what we propose is to have an overlay approach that allows us to bypass the transit network and to put some control on top of the underlying. This also allows us to have a homogeneous view of a heterogeneous set of devices, because the technologies, the access technologies, for instance 3G or Wi-Fi or the Ethernet cable you have in your home router, all those technologies are emasculated over a common homogeneous view that is what the overlay offers you. Also, since you have lots of controllers, and these controllers need to get the state, you will have a large number of southbound messages. And you need a controller that is able to scale out to handle this large number of messages from the southbound. Also, you want that this controller, besides being able to scale out, you want it to be decentralized and symmetric. Why? Because these end nodes are anywhere in the network, and if you are able to offer a controller that any node any controller node can serve any end node, the end nodes can choose the controller node that offers less latency, and if an end node moves, can go and then take another controller node. Also, in order to do that in an efficient way, you need a connectionless southbound. In order first to don't put so much state on the controller, given that we have a large number of controllers, and also to be able to instantiate new instances of the controller and move seamlessly end nodes to these new instances. And since the end nodes will appear whenever they want, you need a pool-based mechanism. So instead of pushing the policies down to the end nodes, because maybe they are not there when you have the policy for them, what you do is you store the state on the controller, and whenever the end node is ready to get them, it will pull the state from the controller. Also, and this differs with common SDN, is that we think that in most of the cases, for end nodes is enough to have IP granularity. At least for the use cases that I described before, IP granularity is enough. You don't have to go deeper than that. But of course, maybe for your use case you need more fine-grained granularity, you can do that, but you have to tune then your architecture to be aware that you will have more southbound messages, that you will have to deal with more state and with more burden in the controller. And finally, the best way to deal with this large number of controlees and with the low traffic quality that they present is to offer an intent-based norm, because in that way you don't need to define policies per each node or per each traffic flow. Particularly, we propose is to have a language base in groups, so you define common policies for a whole group. Whenever a new node shows up, you assign it to a group, and then the policies that applies to that group will apply also to this node. So this is a table that summarizes what I've said. So this is always up to discussion, but we have tried to match challenges to this design principle that I've said. So, well, you see that to overcome the in-place network, you have to deploy an overlay. To deal with the large number of controlees, you will need a scalar architecture that allows us to deal with the large number of messages, and with a connectionless southbound that doesn't put much state, and with an intent-based norm that doesn't force you to define policies for all these controlees. In the same way for the low traffic locality, but with the low traffic locality, you can also take advantage of IP granularity. For the scattered nodes and the transient devices, these characteristics that end nodes have, you use a decentralized and symmetric controller with the connectionless southbound, and in the case for the transient devices, you also want to have a pool-based mechanism. So this is just an overview of the architecture that we envision. I will not put much effort into the details here, and if you want details, you can come and try to reach me afterwards, because we have things in the architecture, and I can give you the details of how everything works, right? But what we propose is to leverage on a controller that has a network interface based on Cassandra. So we take advantage of all the effort that the database people have done and all the research that is in the database world. We use the Cassandra database to store the state, and we put controller nodes decentralized and symmetric that access that state on demand based on the request from the southbound. We use a zookeeper subsystem to manage these nodes among themselves and to coordinate them, and to decide when they have to instantiate a new node, and when the load is low, they can destroy an instance, and so on. For the normal, as I say, we use an intent-based language, and for the southbound, we propose to use a first netconf for the bootstrap of the end nodes. Netconf is connection-oriented, but what we do is that when the node shows up, it connects to the controller through netconf. Netconf provides the initial configuration, and once the initial configuration is there, the node disconnects the netconf session and uses the list protocol to retrieve the state of demand. Using list, you don't have to keep a connection with the controller, and you can pull on demand the state whenever you need it, and from wherever you need it. And finally, the end nodes are in the share overlay that provides an homogeneous view of the data plane. So we would like to ask you guys, what do you think about this scenario? If you think this is relevant, if you think that we are missing some challenges here, or if we think that another design principle is needed. And also, we would like to ask you if we should work on this scenario for the Sdnrg. Finally, I have a demo available that I'm not able to show now for time constraints, of course, but if you have interest, I have it on my laptop, and I can run it for you anytime. So just try to catch me. I will be available on the break. So if you want to see a mobile EndNote as the one I described, or a data center managed by Lisp and over KVM, just go find me and I will show you how it works. So if you have questions or comments.
Mehmet with Comcast. So two questions. One of them is you don't mention availability. I assume it will be one of your bullet items to pay attention to.
I think I didn't get the last part of what you said. Can you repeat that?
The one of them is the availability or reliability. I didn't see in your list. Probably that should be one of the topics that needs to pay attention to.
Yeah, so the availability on the controller part is ensured by Cassandra, by the Cassandra mechanism. So we leverage on the mechanisms that are already there. So we don't propose anything new. And for the southbound, Lisp control plane has mechanisms to keep the state consistent and to be able to refresh and to update the state when there's a failure on the data plane. And you have to think that here those mechanisms are not instant, so there is some delay there. But for the scenario that we are considering, it's not critical. For instance, that some packets from your smartphone goes first through 3G before going to Wi-Fi. So there is a trade-off that you have to do, as always.
Okay. The other question is just clarification. I don't know why you want to add the Lisp on top of the netconf.
No, it's not.
Can you clarify that?
Yeah, maybe I didn't explain myself well there. We are not using Lisp on top of netconf. So we are using first netconf to provide the Lisp configuration for the EndNodes. And once that is done, we close the netconf session. We don't use netconf anymore. And from that point on, we only use the Lisp control plane.
I see. Okay, thank you. The last one is, in the northbound, you have intent-based API. So now I'm assuming that you have orchestration at the top, then you have intent-based APIs talking to the orchestration. Is that what you're thinking?
Yeah, basically that's some of the idea, yeah.
Hi, this is Bhuvan from Verix. This is regarding your overlay approach of taking traffic to the controller over the transit network. I think it may introduce a performance overhead. Maybe one approach to solve this or to bring in the homogeneous view is that you still can have a controller managing different network domains, and you can enable a controller federation so that it can provide you a homogeneous view to the application. So that is one thing I thought of sharing. You can even consider that.
Okay, yeah, you made a good point. I like to think of this some sort of the federation. Well, it's not a federation, but you have a distributed controller on top that you scale out as much as you need. So it's like it's an inherent federation within the different controller nodes that you have deployed.
Yeah, it's a matter of performance overhead is what I'm concerned about. Yeah, probably you can think about. It again depends on the network size, the transit network size, so it shouldn't introduce additional overhead on the performance while steering the traffic is the point.
Yeah, absolutely. That's correct. So using an overlay always increases a bit the latency and overhead in in the data plane, but it's a trade-off that we think is worth to make for this scenario.
So, this is Diego Lopez. The situation is that this is precisely when you mentioned the overlay, you was, I guess, replying what I was going to ask. It's precisely that since you require a tight synchronization among the different controller instances, you were assuming that the data planes was completely uniform. I mean, there was no heterogeneity between the different sections or segments of the data plane, right?
From a logical point of view, there is a homogeneous view of the overlay of the data plane.
Yeah.
Yeah, but you don't need that the data plane actually reacts in an homogeneous mode. So they can react or behavior as they want, and the controller will be able to handle that.
But since you have all the controller instances are coherent. I mean, you're using the zookeeper just to keep the same rules everywhere, right?
Yeah, but not all the controller instances will have all the state. So we put the state on Cassandra, and then you can replicate. Actually, you can tune Cassandra to replicate over the number of nodes that you want to.
So with this architecture, you support different behavior in one of the corner of the networks with respect to the other one, or?
Yeah, because all the state is available from any point. Right. So the only problem that introduces is the latency you have to retrieve the state. But we are dealing here with a scenario that can assume a certain level of latency. So yeah.
I'm Flynn from Nokia. I'm wondering why you chose Lisp over OpenFlow. Lisp is a tunneling protocol. OpenFlow is a control protocol.
Yeah, that's a good question. We use Lisp because actually we are not saying that the architecture that we propose is the only one, or that the choices that we made are the only one possible. You can deploy this also with OpenFlow if you want to, but first Lisp is connectionless, something that OpenFlow is not. And even though that you can use OpenFlow in a pool-based mode, right? So when you have packeting, you send it to control whatever. Lisp is more oriented into be a pool-based architecture. So we are not saying that Lisp is the answer. We are saying that Lisp is an answer, right?
Okay, thank you, Alberto. So next speaker, please.
Hello everyone, good afternoon. This is Zhenbin, English name is Robin. So today's the topic is Inter SDN in seamless MPRs for mobile backhaul network. Okay, next slide.
You have the power.
Okay. Okay, I think this is some of the background introduction. And the seamless MPRs network has been proposed many years before. That is try to integrate the access network with the IP core network and the metro network. But later, the seamless MPRs architecture is proposed to integrate the mobile backhaul network and the IP core network, because later that the mobile backhaul network is also MPRs based. So when this mobile backhaul network is integrated with the IP core network, so there are many the huge nodes in the network, and the scalability is a very big challenge. So that they introduce some of the solutions such as the label-based BGP to allocate the prefix multi-domain and also and also some of these IGP multi-areas to reduce the scale of the network. So this is the seamless MPR's solution. And also later the SDN has been proposed. This is try to used for the traffic optimization or simplify the network management and operation of the network. So then when SDN, because in the traditionally and the SDN is used for the data center and one and this one. This is always a single domain. But when the controller SDN is introduced in the seamless MPLS network, because it has multi-domain, maybe has IP core network and different mobile backhaul network. You cannot use one controller for the whole network. So there must introduce the multiple controllers, the architecture to solve the possible issue. So this document is just try to propose the possible architecture for the inter-SDN for the seamless MPRs in the mobile backhaul network and identify the possible challenges and the requirement to be researched. Okay, next slide. Oh, sorry. I always forget my power. Okay. I think this challenges that is the first is from the architecture. I think this is because this is a larger scale network. According to the original, the seamless MPRs is said that is must taking into account the scalability of the thousands, 100,000 nodes in the network. So that is the scalability is a very big challenge. So the SDN architecture, we must think about the possible the hierarchy SDN controller architecture or the peer this SDN controller architecture. So this is we say because of the multiple controller, we must think about the scalability of the controllers. And also that is because there are multiple controllers, so how to divide the different functionalities in different controller and the different layers of the controller. This is also must be taken into account. And also that is the different controller, they have the orchestration because of the multiple controller, the different functionality, how to interworking together. So this is also the possible challenges. And also that is because this is why we use the inter-SDN for the seamless MPRs mobile backhaul, because they wanted to do the end-to-end the traffic optimization, because they have the multiple alternative paths in the network, so that it can have a better choice to satisfy the quality of the service of the mobile service. So that is this is the but when seamless MPRs are introduced, so we must think about the inter-domain the traffic optimization. So this when we when the SDN is used for this purpose, so that is the following things must be taken into account, and also this related with the algorithm. The first one is the topology abstraction. So that means how to abstract the topology in the different layer, so that is make the less information in the up layer, and the down layer they have the detailed information. So this is how to abstract the topology. This is the algorithm specific. And the second one is the end-to-end traffic optimization, because there may be multiple the underlayer controller for the optimization, and also they have the super controller for the end-to-end multiple end-to-end the traffic optimization, how they can work together. So this is okay, and this is the third one is just also based on this one, the optimization, how it can be interworking together. Okay, and also in the architecture, we will go on to identify the requirement which is lack in the existing solution, because in a larger scale network, we must based on the control protocol such as the existing the IDP, BGP, or the PCE, such as the protocol. But these protocols, when taken into account the inter-SDN architecture, so we can identify the possible requirements and the new requirements for these traditional protocols. Okay, next slide. Sorry. Okay, this habit. Okay, I think this is the. Okay. Okay, this is the inter-SDN, the architecture is the introduction. Okay, so here we identify this is the seamless MPLS network. Here? No? Okay, so here is the seamless MPLS network. So here we can see has multiple IDP area, and here we have the ABR, so that they use the BGP to span multiple domains. So this is the larger scale seamless MPLS network. So when we think about the architecture, we have comparing the different models. The first model is the hierarchy model. That means the subcontroller to control one domain, different domain. And is a supercontroller that is to set up the connection to each subcontroller. And in this the architecture, there's no connection between the subcontroller. So this is the pure hierarchy architecture. And another option is that use the peer controller architecture. That means the connection will be set up between not only between the supercontroller and the subcontroller, but also the connection is set up between the subcontroller. But finally, we, according to our analysis, we think the hierarchy is better. I think that because if the peer model is introduced, there need the full mesh connection to be set up between the subcontroller. There will be proposed scalability issue for the controllers. And also we think this is like the star model, this hub spoke, like this the model is introduced. So all the information can be reflected through the supercontroller. I think this is also the traditional way for the BGP route reflector. So we think this hierarchy architecture does work. Okay, and then this is the different components is identified, and the functionality is divided in the subcontroller, supercontroller, and the orchestrator. Okay, and here is the subcontroller. Subcontroller has detailed topology information for each domain. So this is for the subcontroller. And also it be responsible for the traffic optimization for each domain. And then the supercontroller it for the subcontroller need advertise the topology information to the supercontroller. So the supercontroller has end-to-end the topology information of the whole network.
Yeah, I just want to ask a question.
Yeah.
Before you go on. So does the supercontroller have all, like sort of the union of all of the information, or does it have some abstraction? That's my first question. Of all the ones below, the subcontrollers. And then the second one is, have you thought through the CAP theorem kind of implications of the distributed system that's kind of implied by all of this?
Okay, I think regarding this, the first one I will introduce later. That is when the topology information is advertised to supercontroller, it need abstract information either to advertise from the subcontroller to the supercontroller. Yeah, all else there's no that is make no sense of the hierarchy because there's no abstract. So that's my point. Okay, but regarding your second point, I'm not.
Okay, well we can take that one offline.
Okay, yeah. Okay, so this is the supercontroller, and also that is this another is the orchestrator, because in the in the network, in order to the run of the network and the supercontroller need the configuration and also the BGP and the IGP VPN like this one. And we also need some of the orchestration between the supercontroller and the supercontroller. So here we have the orchestrator. It can provide the intent-driven the method to deploy the possible configuration to simplify the network management. Okay, so here we introduce the possible procedures. So, okay, I think the first is each domain. That means each domain is the traffic optimization. The second one is the end-to-end traffic optimization. The third one is the end-to-end service provisioning. And the last one is the auto discovery. Okay. Okay, I think this I have introduced because we identified that the IGP and the BGP link state can be used to collect the network topology information for each domain to the subcontroller. So I think that when do the traffic optimization, that the subcontroller act as the PCE server. So it based on the collect the IGP topology information, so it can do the path optimization, so that it can implement the traffic optimization. Here we propose two cases, and this is the two cases is PCE. The first case is the PCE initiated the new path calculation. So the path will be sent to the PCC to re-optimization the existing tunnel. The case 2 is the PCE initiate the path calculation and set up the new LSP will be created in PCC without the tunnel configuration. Because this is the difference is because the currently that the MPLS-TE is based on the network configuration. But now that the PCE initiated LSP has been proposed, so the LSP can be triggered set up through the PCE without any network configuration. So this can simplify the network management. And also there are the two sources, under the MPLS-TE, the optimization can be triggered by the BGP LSP optimization, because the optimization is based on the service, because the up layer is the BGP. So here that is the different cases. Okay, the cases is means that if the reuse the existing tunnel, so it's just to optimize the MPLS-TE tunnel without no extension of the BGP. But the case 2, the problem is that maybe when they do the traffic optimization, we need to set up the new MPLS-TE tunnel. When the new MPLS-TE tunnel is set up, so the BGP route has to change to the new tunnel. So the BGP extension has to be introduced to implement the change tunnel for the BGP route. Okay. Okay, I think this is the end-to-end traffic optimization. In the seamless MPLS for the end-to-end traffic optimization, this is just a label BGP tunnel, because this is BGP LSP will span multiple domain. Okay, and here we use that the first one, the supercontroller will set up the BGP to the subcontroller, and the subcontroller will set up the BGP to the each edge node for each domain, so that all the edge node it can reflect can advertise its route to the subcontroller, and the subcontroller will advertise the route to the supercontroller. So the supercontroller can have all BGP route information. So based on this route information, it can determine which one is to be optimized. And also that when do the traffic optimization, it must be based on the topology information. I have introduced that is the topology information also need to get from the network and the subcontroller. And also that we compare the two methods. The first method is all topology information is collected by the supercontroller. And the second one, we think that is use abstract topology information. So we prefer the option 2. But this also will introduce another challenge because this is the abstract topology information. So when do the end-to-end traffic optimization, there may be lack of the enough information. So it needed to do the traffic optimization based on the interworking between the supercontroller and the subcontroller. Another way, if the all topology if available in the supercontroller, so all the end-to-end traffic optimization can be done by the supercontroller's own. But this solution is not scalable from our point of view. Okay. Okay, I think this is the next one is the traffic optimization for the label BGP. When the abstract information, topology information is available and the whole BGP route information is collected in the supercontroller, so it can make the decision how to optimize the traffic for the end-to-end the label BGP tunnel. Okay, and here this is the end-to-end service provisioning, and I think that the first one is the MPLCT tunnel in each domain. So we, because this is a very large scale network, we tried to simplify the configuration as less as possible. So here the T tunnel, we prefer use the PCE initiated LSP to reduce the configuration for each tunnel. And for the label BGP, we think the label BGP always the sedative configuration. We don't want to do the configuration on demand. A third one is the L3 VPN and the L2 VPN service provisioning. We prefer that the model-driven solution, so that it can map the abstract the northbound model to the southbound the node-based model, so it can simplify the L2 VPN and L3 VPN service provisioning for the user. Okay, here this is just a small, because as the number of the controller in the network is increased, so there may be introduced the auto-discovery mechanism of the different controller. So here we see the two requirements. The first is the role of the different component, and also another is the capability of the different component, including the supercontroller and the subcontroller. This can be advertised through the IGP or the BGP link state, but this one is not identified in the current IETF. Okay, so this is the next step. So we, in the first draft and the phase 1, the research, we identify the possible the scalable network architecture, Sdn architecture for the larger scale network. And also that is more research work is going on. So I have identified, for example, the topology abstraction. This is the algorithm specific, and also the interworking of multi-layer based traffic optimization. And also that is the requirement and the extension of the existing protocols such as the IDP, BGP will be proposed. Okay. Okay, that's all. Any question?
By the way, who has the blue sheets? If you haven't signed the blue sheet, raise your hand so we can route them in your direction. Okay. Thank you. I guess we have time to take one question, right? Okay. Please.
I'm at with Comcast. You certain architecturally you can have subcontrollers and the supercontrollers and so on and so forth. But certainly, I'm not too much enthusiastic about having too many layers to deal with. What is your thought? When do you think you will really need a supercontroller? And when I look at your diagram, with subcontrollers like a per node basis, so am I misinterpreting what you have? So give me some ideas. Why do you think when you need the supercontroller?
Okay. Okay. I have introduced this idea in this one. Because if we want to use that, if we use the server controller, this is only one layer architecture. But because we have some of the end-to-end traffic optimization, so we have to set up this full mesh connection between the server controller. So this is as the number of the server controller increase, so there may be proposed scalability issue. So that in order to solve this issue, we use the super controller. So this is a two-layer, the architecture that can always, the information if we need to exchange between server controller, it always, this goes through the super controller. So this is our point of view is for the scalability. Yeah, this is reason. Yeah.
Okay, one more question, if it's quick. Yeah, that would be you at the mic.
Where?
I'm from Netcracker. The router between the two domains, the ABR1, for example, it has two subcontrollers. So which one will configure the cross connect between the ingress and egress path?
Ingress and egress path. Sorry.
Yes. So some routers are gateway between the two domains.
Yeah.
So what controller will configure the routing for it to cross connect the?
Okay. I got your point. In fact, in the seamless MPRs, I think this need some background knowledge, because this at the beginning, so that is the seamless MPRs that use MPRs, the technologies is set up the connectivity between any pair of nodes, because they at the beginning, for example, this is the PE. They have here, they configure the label BGP, so that the label BGP can directly to advertise the prefix to each node, so that each node has the label BGP RSP. So this is the ingress can be here, can be here, can be here. So that any two node, the connectivity is always available. Is not needed to configure.
Okay.
Yeah. Okay.
Okay, thank you, Robin. Could we
Thank
have
you.
the
Okay,
next
thanks.
speaker, please?
Okay. Remember your power.
Who's next?
Catalin?
Okay. Thank you. Good afternoon. My name is Catalin Meirosho. I'm with Ericsson Research in Sweden. And I will be talking about some joint work that we do together with two research institutes in Sweden as part of an EU-funded research project. When we look at the monitoring today, we realize that we've defined in different standardization for us a lot of tools that are very nice. They have been crafted for providing particular levels of details, and they've been attached to a whole bunch of handles that were very well optimized so that they are operated manually. And the issue with this is that when the need for monitoring scales with hundreds and thousands and hundreds of thousands of nodes that move around in a software-defined infrastructure, these type of handles don't allow us to have a very flexible control over the nice monitoring functions. The other issue is that we have a scalability problem with respect to how to disseminate information out of this network functions, network monitoring functions. The work that we are doing is part of an EU project called Unify. This is a project that has a few operators, a few vendors, and a few research institutes and universities in it. And we work to increase velocity of service introduction. And And we also develop a set of novel observability and verification features, and the presentation today is going to focus on the observability features. So the first thing that we try to do in this project with respect to observability is to take a split architecture approach for defining monitoring functions. And the way we take that split architecture approach is to have a concept, so take the concept of a universal node that we have in the project, and you can imagine that a universal node, it's a fairly big server, a lot of CPUs, a lot of network cards installed in it, maybe some acceleration features, with everything managed through this universal resource manager. And inside this universal node, there is a virtual switching environment, and there's a VNF execution environment. From a monitoring perspective, what we would like to have is a local component in the data plane that provides, for example, access to counters. It also provides low-level monitoring actions, such as inserting probe packets into the data plane if need be. Then, on the local control plane, which can be placed either in the VNF execution environment or together with a universal resource manager of the node, we perform a set of actions that are, for example, aggregation of counters and inspections of the local observability point components. We will do node local analytics and management of the monitoring behavior. And overall, there is a control app that would do this management of the monitoring behavior for wider set of nodes. Now, in order to have these features at the local data plane and support the control split, then we need advanced programmability features that should be available. And in terms of more generic requirements, what we need is access to deploy and implement the data plane monitoring components that we want, more expressive programming capabilities. We need better scalability for the way we disseminate the information that we collect from these monitoring functions, and we need an easier way of integrating with information consumers. And these information consumers, they are no longer just a network management system that takes information out of SNMP, is no longer only the OpenFlow controller that reads counters through the OpenFlow protocol. These information consumers could be any kind of virtual network functions. They could be other monitoring functions. So I will start by telling a little bit of what we've done in order to address this scalability of the information dissemination. And what we've done is to work on defining a monitoring bus. We realized that there is a lot of work done outside in the community on defining very efficient buses that actually take this feature. And there are a lot of advantages of choosing something like ZeroMQ for this task. In terms of advantages, we see that there are multiple transport protocols that we can use, and therefore we can adapt the transport protocol for exactly the receiver of the information or the producer of that information. If we need to communicate between several threads of the same application, then we can use the same monitoring bus with the IPC bindings. If we need to communicate between several nodes, then we can use the TCP/IP bindings. There is a reliable multicast binding as well. ZeroMQ also has a really big support for programming languages. If you want to write in C, if you want to write in Java, if you want to write in Python, if you want to write in Perl, you can write in any of these languages and more. So that's very interesting. And then it's a high throughput, low latency communication. The disadvantage is there is no message persistency, there is no high availability, and there is no guaranteed ordering, which you would get if you'd have the bus implemented with something like RabbitMQ, for example. But for the type of information that we'd like to exchange with this bus, we don't need that capability. If we would need to have it, then we can choose either to implement it in the 0MQ bus, or we can have a gateway to a RabbitMQ bus that would provide that functionality. And the way we implement it in Unify is to define a set of a hierarchy of brokers, and these brokers, all of them connect to different types of 0MQ sockets. A dealer, it's a 1-to-N communication socket. A router, it's an N-to-1 communication socket in 0MQ. Within a universal node, we can use an interprocess communication between some monitoring functions, between several universal nodes, or between a universal node and the orchestration, we can use TCP/IP. So what we've done as part of the Unify project is to define these brokers in a fairly simple routing algorithm that is quite scalable. Now, as an example of a different type of monitoring functions that requires some more advanced programming capability, but can provide additional information if additional features are present in the data plane, I have here a function that actually uses two counters for the first and second order moments. So so for the first and second statistical moments for link utilization, the way it was implemented is that in the virtual switching engines, we have the reading of the counters. In the local control plane, we have a set of modeling capabilities, and then a control app does the link utilization. Now, in terms of what is the use for this type of functionality, we could estimate, for example, the risk of congestion. And the graph here shows the risk of congestion on a link. It's a 1 gigabit link from a network in Sweden with a trace that was 9 hours in terms of length. And with a 5 minutes estimate at the modeling level of the function, we're able to predict quite well 300 milliseconds congestion intervals in the on the trace on this link. So with this type of function, we don't need to read the counters n times. We just need to read it every 5 minutes or so from the estimate. So we are able to cut significantly the traffic that would be needed to estimate the same type of parameter just by reading open flow counters or SNMP counters directly from the port. Going to the next level, we will need to connect the information that is provided by monitoring function by monitoring functions with orchestration and with the controllers. And this is a very generic view of the Unify architecture that my colleague Robert presented in the Sdnrg in Hawaii. The architecture has an orchestration layer and a set of controller adapters and a set of controllers at the infrastructure layers for compute resources and for network resources. And what we are doing is to define as part of the reference points between different layers in the architecture a set of APIs that take as parameters network function forwarding graphs, identifiers, and a set of metrics that need to be measured at the layer further down. And then we are able to get the performance values, set notifications, and verify a set of parameters on this architecture. So in conclusion, we think that the scalability of monitoring can be improved by using monitoring buses instead of the standard ways of disseminating information through SNMP or through the counter-related parting protocols such as OpenFlow. We believe that adopting split architecture principles for certain monitoring functions would also help with the scalability, because it limits the amount of data that is disseminated all the way down to a big management agent out of the node. And then we see the need for more flexible data plane programming capabilities that would allow us to have different types of counters implemented, different types of probe packets than the ones that are defined right now as part of the standard. And we also need more expressive programming capabilities as part of the interfaces between different layers in the orchestration and the controllers. So, thank you very much. Are there any questions?
Okay, thank you very much. I think one general observation really for the presenters today is there's a wider audience within the IETF, Sdnrg, who either can't participate locally or unable to dial in and attend remotely. But it's worth sort of hosting the slides, well, we host the slides anyway, so you can point to where the slides are currently. But if you send an email to the list and just outline sort of the current research challenges, where you're investigating, and how people might want to participate, I think that would be really useful.
Yeah, we'll do that. Thank you.
Germany.
Hey, Diego.
Yeah.
Diego.
Diego Lopez. Catalin, when you mentioned this more flexible data plane programming, I assume that if you are distributing, or you're using pure software-based data plane elements, you would be able to make some kind of, I don't know how to call them, probes on purpose.
Sure.
Precisely fit it for a certain purpose, deploy them, and then and deploy them when you have monitored enough. This is something that you have in mind in the architecture?
Yes, so this is something that we have in mind, that we would need, let's say, it's either software data planes, and for that it could be virtual switches, but it could also be extensions on a programming language like P4 and very flexible forwarding chips that people are discussing, and I think that there was a presentation in some earlier Sdnrg on some of this technology. So it's either or.
Okay.
Eric Nordmark, oops, that's loud. So I imagine that the people that are working on large-scale data centers have scalable infrastructure, monitoring servers, etc., right? Their applications, whatever it might be. Is there a body of research there that sort of, I don't know how much of that is actually published, right? But do you know whether there's a body of research there that one can leverage and see, okay, here's how they do things with servers, and compare it with what you're thinking about for the network side of things?
I think that there are articles that were published by Microsoft Research, and I think Google also, about a little bit about monitoring in the data center. Now, the way they do it is to take all the data that they want and put it in a big database, like a Cassandra database or a MongoDB, and then run a set of analytics algorithms centrally, or execute them distributed, but on the centralized database. What we try to do with the monitoring bus here is to allow at least some of the virtual network functions direct access on the information as soon as it gets onto the bus without the need for that information to be first stored in a database.
Okay, that's helpful.
Okay, thank you very much, Katalin. Thank you. Next speaker is Yoshihara-san.
Okay, thank you. My name is Koshiro Mitsuya. I'm not Yoshihara, sorry. So I'm going to introduce our recent work about the network management system, or let's say about the network management application. So the title of the draft is Network Configuration Web API for Bandwidth Reservation. So this is a brief overview of our network management application that regarding a situation, for example, web application requires a certain amount of bandwidth to his infrastructure. So motivation, although network becomes more programmable today, only operators use the technology for their purpose, maybe for cost saving or service provision speed quickly. Then our motivation here is to let application or end user take more advantage of the programmable networks, not only for operators. So we believe this is going to be a key factor to provide a better user experience for future networking. So basically our approach is something like this. So user define a simple policy and the system calculates the configuration for them instead of them. Then system automatically deploys them. So in conventional network management, each organization runs their networks under their administrative control, and those networks are interconnected. So that's okay. Today's, as you know, the network became more programmable, but we would like to put a new type of network management application on top of the programmable network to use their function from application or normal end user, which is not operators. So once user describes their high level of demands for networks, our controller takes care of the deployment of the virtual network that satisfies and that meets the user demands. So we call this kind of operation system SDN, Service Defined Networking. Here, service means default networks provides various functions, and service specification is a user policy or user demand. So that that is concentrate or requirements for the network cases. So in SVN, for example, app depends. I want to receive 4K streaming from YouTube. This is a service description in our researches. Then the service description is compiled to the actual network configuration automatically by system. Then the system deploy it. So this is our our word in my mind. Okay. So there's many research topics to achieve this word. Then we introduce some of them in the draft. So which is languages to describe the policies, and also web API to manage the policies. So from here, I will show you some example of the service description languages and also some scenario how to use the APIs. So this is a topology we using to describe language for the example. So I forget to put the note from here on the slide, but this is a virtual network that build on several physical networks. So this network described as something like this. First, we list nodes, then we describe where is a node should be located, then which node is on the same link, then what kind of service you want to receive, something like this. So with the network description, we also describe our services. Then on this example, we describe network address information, but we can skip it if you don't want to specify it. Then also here, you can describe some services eventually or consistently. So this example is for bandwidth reservation. So you can reserve the bandwidth from address A to B with 10 megabps, something like that. So this is a scenario what we have. First of all, our controller know the topology and physical resource information somehow. We call it topology database. Then we provide, let's say, network administration provide simple policy to configure the virtual networks. That is NDL, SDL I presented later before. Then system calculates the actual configuration. Then system deployed. So virtual network has been deployed from user policy. Then application required, for example, bandwidth through our API. So system also calculate configuration based on the application requirements. Then this configuration also deployed automatically by system. The application now get a better path for the, for example, video streaming, something like that. Okay, so SVDN is a new type of network management application that let application or the user can take advantage of programmable network, SDN or NFV, whatever. So now we are developing proof of concept to confirm the benefit of system on campus networks and also commercial data center. We are using open flow NF backbone to connect them. That's it. Thank you.
Well, thank you very much. Are there any questions?
Ken Calvert, University of Kentucky. So in your web API, your web interface, what kind of authentication will you do, and also what is the granularity of the configuration you install? Is it host to host, or how do you specify it?
Okay. Right now we don't have any authentication mechanism on our API. And so this is just a proof. We are now just developing proof of concept. So maybe we need to do more work on that later. And also, I'm sorry, I didn't get the second question.
So you will install state in the, you'll have the controllers install state in the switches, and what's the granularity of the reservation? And is it a 5-tuple or address pairs or what?
Right now, we reserve the bandwidth using 5-tuple, and the
maybe we can. I'd like to talk to you.
Yeah,
after,
thank you.
We're doing something similar on our camp.
Okay, thank you.
Okay, Robin from Huawei. I need two things to be clarified. Can you preview slides? Okay. Okay, this one. So here, the first one, the web API, it seems only the destination. There's no ingress. It just means destination. Okay.
I'm sorry. Maybe this is a bad example. I mean, destination.
Yes, seems only destination, because I think when the bandwidth is guaranteed, maybe between one specific ingress and the specific egress.
Yeah. So we need to add such information on the slide. I think this is my mistakes.
Okay.
Yeah. Okay, thank you very much. One final comment is there was a new working group that was chartered in the IETF, the routing area. It's called Layer 3 Service Model, L3SM. They're looking at a Yang model for describing a Layer 3 service request from a customer to a network operator. So you may want to investigate that as well. Next speaker, please.
Okay, thank you.
Skurong.
Okay, good afternoon, everyone. I'm Ronggu, and my topic is about my draft of Sdn controller requirement. And at first, I want to introduce our public cloud and private cloud to you. And the public cloud and the private cloud are provided in China Mobile, aiming at the government customers, large enterprises, and financial customers. In the right bottom is the picture which we can find in the website. And in the actual deployment, we do find some problems, such as the bottleneck of the VLAN numbers in large layer 2 network of cloud data center. And besides, in the VPC service, not only switch could support isolated forwarding table, but also the firewall and load balance should also support them. And besides, we face the concurrent configuration problems, because actually multi-tenants are configuring the network elements at the same time, while the configurations of the network elements are pushing down so slowly at the same time. What's more, as we use multi-vendors network elements in our network, so we face the problems that different network elements have different command lines. And last but not the least, the physical devices such as the firewalls and load balances, they are of low utilization of the resources, which may cost a lot. So we need to search for a more intelligent and agile network solutions. So we find the Sdn network with the features such as the scalability, reliability, programmability, intercommunity, and security. And then we divide, as we know, the SDN controller may be the core entity in the SDN network, which act as the role such as the brain in your body. So we come up with the requirements of the SDN controller. We divide the SDN controller into several parts, such as in the architecture. One is the protocol subsystem, forwarding abstraction layer, and route management. These are fundamental requirements of the architecture. The protocol subsystem means the southbound interface, and the forwarding abstraction layer is working on translating the difference forwarding plane into the unified interface upside. And the route management, which is working on the centralized computing and the forwarding path calculating. Besides, there are also topology, host, flow table, and interface management, which we are required. And then the database subsystems and the OAM management part are also needed. Besides the internal application subsystem, which is also the interface to the OpenStack, is also required. Besides the architectural requirements, we also come up with the requirement of functionality. Now, in our data center, we have hundreds of computing nodes, which will increase to thousands this year. And also the VPC and NFV services will be introduced in our data center. So we come up with the requirements of the functionality. One is the multi-tenant self-service and network function. As we know, multi-tenants are existing in one data center, and what is desired is that the tenants can share their same IP address. Besides, the tenants, one tenant may have one subnet and maybe two or more subnets. The virtual machines between one subnet, they can communicate with each other, while the virtual machines across the subnets, they should communicate with each other through one router. So these are the network function requirements. Besides the router and the floating IP and the NAT devices are also needed. And the ARP broadcast storm suppression should also be taken into consideration. And for the administrator and the network management, we think the administrator should gather all the information such as the tenants and the network and the relationship between the tenants and the network. And for the network management, we think that the network topology information should be gathered. Also, we think that the SDN controller should have reliability and scalability, which means the SDN controller should be reliable and scalable. About the performance of the SDN controller, we try to find some indicator values in order to evaluate the SDN controller, such as the number of the forwarding nodes the SDN controller can support, and the capacity of flow table per controller node, and the time of the forwarding table processing, and the time of establishing the forwarding table, and the standby time of controller nodes. Here I list some part of the test results. The first line is the baseline. The baseline means the minimum number we required, and the maximum line means that the actual test results we tested in our lab. Maybe there are some more indicators of the performance we should add here. If you have some advice, you can tell me. And about the northbound and southbound interface means that the SDN controller should support the basic protocols. and also the SDN controller should obey the procedures. At last, I want to give an introduction of the SDN use case in our data center. Maybe it's beyond the SDN controller, which is listed in my draft in the SFC work group. From the figure we can see, from up to down, it's the VPC and the service chain application, and then it's the orchestration. Now we use the OpenStack, and then the controller. And in the bottom is the network elements, such as the physical switches and all the virtual switches and other devices. And when we, in our actual deployment, we found that there are some challenges. The first one is about the host operating systems. Now we use the CentOS and the Red Hat in the, as the host OS in the OpenStack controlling and computing node, while it turns out to be that the Ubuntu is more mature. The second one is that now the interface of the OpenStack is limited. So the extension of the northbound interface of the SDN controller should be taken into consideration. And the third one is that in designing the architecture, we think that the service function chain should also be taken into consideration. Then about the next step we are still keeping on researching on the northbound interface of the controller. And besides, we are focusing on the architecture combining SDN and NFV. At last, any comments and suggestions are welcomed.
Okay, so we have one question.
Hi, this is Bhuvan from Verix. So I have three.
I'm sorry. Oh.
Hi. This is Bhuvan from Verix. I have 3 points here.
Okay.
So the first is the architecture. So
architecture?
That you have described.
This one?
It is based on your slides.
Okay.
So
this one?
This is almost sort of defined in RFC 7426. So how is it different is one. And second point is you talked about the performance requirements, which is already quite in discussion in the benchmarking group about controller performance benchmarking. And number 3 is you are talking about the interface to OpenStack. So what about other interface? Are you only restricted yourself only to OpenStack cloud orchestration or to any other orchestration? So these are all 3 points I start to
the first
get it clarified.
Okay, about the first one. About the first one is the architecture requirement. Now we list the architecture requirement according to our actual deployment. This is the basic requirement. Maybe the RFC you mentioned, we can evolve them to it. But we think this now this requirement is what we need.
Yeah, I believe this RFC is already evolved from this forum itself, I guess. So
okay.
Yeah, probably you can have a look at it.
Okay, thank you. And about the performance here, I also take part in the benchmark work group. It really helps me a lot. And I have read about your draft about the SDN controller performance test. We do think that it also help us a lot. But now we test only these indicators. Maybe we can discuss later about your other indicators, which may seem very important. Okay.
Probably will discuss.
And the third one is the OpenStack. And now, as we use, what we use is the OpenStack. So the interface, the extension interface, we are considering maybe focus on the OpenStack. Maybe later in the research, we can research other, the integration with other orchestrators.
Yeah, it will be good approach when you try to standardize. It needs to be a standard interface, probably RESTful or things like that. So rather than just focusing on one, integrating with one entity, so that limits the scope. That is the point.
Okay, thank you. Thank you for your suggestion.
We might ask us a quick question. I'm not with Comcast. Could you please elaborate on the limitation on the OpenStack or the northbound interface?
I'm sorry, I beg your pardon. The limitation of OpenStack?
Right. What issues that you came across? What limitations that you have?
You mean why I should extend the interface? Yeah, because as in our service design, we think that the NFV services are also what we need. While in the OpenStack, we find many other functions the interface do not support, such as the high availability of the virtual machines. Yeah, it's not in the OpenStack interface now. There are many other interfaces which we need are not listed in the OpenStack file. I have an Excel which detailedly lists all the interface I need compared with the OpenStack. Maybe I can share this information to you if you are interested.
Yes, thank you very much.
Okay, thank you.
Okay, thank you.
Oh, sorry.
One very quick question.
I was just trying to capture notes. Can you please bring this into BMWG? Sarah Banks, VSS, chair of BMWG. Please bring this in. I didn't know you were going to bring this in here, otherwise I'd have corralled you earlier in the week. But I would really like to see this come in because, as you mentioned, the draft is there. So anybody interested in SDN controllers, we've got one going in BMWG in terms of how to benchmark them. But you've got results, which is awesome.
Okay.
So please bring them in.
Thank you.
Thank you.
Yeah, I'm glad to.
Thank you.
Okay, Carlos.
So, hi everybody, my name is Carlos Bernardos. I'm presenting this work on behalf of my co-authors, Luis and Diego from Telefónica and Mohamed from Orange. We presented a first version of this work in PAS IETF. Our main rationale of the starting point of this work is the fact that the current existing SDN proposals centralize the functionalities of different purposes, basically transport and service, and there is no clear separation between these two functions in the controller in the architecture, and this poses different issues like the ones listed in the slide. So basically there is a monolithic architecture where you don't have a clear separation between the service, the control of the service, and the control of the transport network. That leads to additional problems like interoperability issues. You cannot easily reuse components for one service to a different services. This may also drive to vendor lock-in situations. This also makes more difficult to diagnose and troubleshoot your network. So basically, with this starting point, this problem in mind, we came up with this idea of basically creating two layers in the SDN architecture. This is what we call cooperating layer architecture. The key concept of the key idea is to basically separate these control functions of the services and the transport network. So basically the service becomes independent from the transport, although as we will see later, we will need, of course, a tight interaction, tight cooperation between these two layers. So the idea is to have this separation between two different strata, one for the service, dealing with the function related to the service provision itself, and another one, the transport stratum, dealing with the functions required for the data transfer, for the connectivity required to provide a service. This separation, functional strata, we also further compose or group this into three different planes. The control plane, which is in charge of controlling the resources on each strata, the management plane, which is in charge of managing the resources and the control plane in each strata, and the resource plane, which is the actual resources to provide the service. As I mentioned before, by this differentiation, this separation into different layers, a tight cooperation is required between both of them. Here we have a picture showing this idea of this layer architecture. We have the service stratum at the top and the transport stratum at the bottom, and the three different planes. The management and control plane of both strata are logically centralized in controllers. So we have a service SDN controller and a transport SDN controller. The main work or the main research things on this work are basically on this interface between the service and the transport, how we manage to make this API between these two controllers, and also on top for how to expose the service capabilities to external services applications. And then on the left-hand side, we have the resources. And basically, another thing I want to highlight here is that in this architecture, the service controller is kind of a client of the transport controller. And also to highlight that this may be also hierarchical, so we might have that the transport strata itself is also composed of service and transport and so on and so forth. So by having this hierarchical approach, we can also, for example, solve or address scenarios like multi-domain, as we will see later. So topics to address. I already introduced some of them in this architecture. The main topic is, as I mentioned, this interface between the service and the transport strata. And the abstraction requires to expose the transport capabilities to the services, also to transfer to notify events from the transport to the service, and the service to instruct the transport the configuration required in order to accommodate the requirements of the different services. As I mentioned before, also the means to capture the service requirements for external applications. Other additional topics to address in this architecture, well, multi-domain in the transport scenarios. Multi-domain not only in the sense of administrative domains. We may have a transport network that is composed of, to compose a service, we need to traverse different administrative domains, but even within a single administrative domain, we may have different domains, for example, because of technology or vendors, and this requires to be also addressed, something that we want to address. As I mentioned before, recursiveness. We may have a transport stratum that itself is composed of different layers, service and transport. For example, to provide an abstraction at that level that hides the fact that we have different domains below. We may have this kind of hierarchy there. Then we have the security and trust issues in this interface that I mentioned before between the different strata, and of course operation management diagnostics issues. These are also research problems that we want to tackle. In the document, we have a set of deployment scenarios. We mainly consider two families, the full SDN and the hybrid SDN environment. The full SDN environment, we also have different categories. For example, one is in which we have multiple service strata working or interacting with a single transport strata. So basically you have a single transport network that provides provides connectivity to different services. We may have the other way around. We may have one single service stratum dealing with multiple transport networks, strata. So basically that service will have to act as an orchestrator in order to compose the end-to-end service, and we may have different combinations. And also we have another family of hybrid environments in which you may have SDN-based service stratum dealing with a legacy transport and the other way around. In order to be brief, I will not go into more details here. Then the document also is meant to include different use cases. So far, the only one that, well, actually in the document is not yet there, but we have different use cases. One is, for example, NFV, taking into account the HC NFV architecture. We may place these services, the end controller here, dealing with the virtual network functions, instructing them how to act on the traffic, and then we may have here the SDN transport controller, basically providing the connectivity to these BNFs. So this is one example of use case that we plan to detail.
Sorry, Carlos, just to interrupt you. If you're leaving the room, can you please ensure that you've signed the blue sheet? Otherwise we'll follow you home. And there's one here. Is there anyone who hasn't signed the blue sheet? If you can connect, that would be awesome. Sorry, Carlos.
Thank you.
Okay, so just to quickly wrap up, The next steps will be to actually get feedback from the community if you think that is an interesting topic to continue working on. For example, Ericsson Research has already committed to provide some input on the multi-domain use cases. Then we want to document a gap analysis. We have identified here some research topics to address. We need to basically see what is missing and what can be reused. Then we need to complete the documentation of the different use cases in the draft that is still missing that part, and then work on the requirements for the interface definition, and then on the issues that we have listed before. So our idea, the author, is to continue working on this document, and maybe in a future iteration ask for the working group for the research group for adoption of the document if you consider that this is an interesting topic to keep on working. So thanks. Any question?
Yeah, hi, Sandy Veach. Can you say anything about that abstraction layer between your two?
What do you mean by
that
here?
Right there?
Yeah.
Have you any conclusions or any information about the form of information that you would be passing there?
Well, yet we haven't gone into the solution itself. So basically, we want to have the means to be able to abstract here for example, the events that are required for the service in order to compose the service from the transport stratum, and the same thing for the service to the transport, but we haven't got into the details yet. This is basically an architectural document, not a solution document, so that's not yet worked out.
This is Agnet Cracker. This is interesting. I have two comments. Why just two stratum transported service, not multiple layers? Because if everything is service, the lower provide capability and capacity for the upper, then we can have service on top of service. And then we need a separate management plan on the right to manage the connection between these stratums.
So for the first point, well, basically the hierarchy or the recursivity is already supported by the architecture. So you may have this transport strata composed of service and strata.
Yes.
So basically that covers your first point. Your second point, if I got it right, is to have a management plane to manage the different strata, right?
Yes.
So, well, that's something that definitely we can look at and to see whether that's an interesting point. So we may have a discussion on that on the mailing list. Thanks for that point. Thanks.
Thank you. Your question about whether or not this is a topic, or something that the working group might want to adopt goes to this one. So, I was going to give a talk on it on machine learning for SDN, but we're kind of out of time, and this is kind of something we wanted to get to for the group itself, and so I can talk to any of you about that anytime. And my slides, the PowerPoint and PDF are on the proceeding site. So, what is this all about? Well, when we started the Sdnrg, when I wrote the original charter, I wrote it sort of like a IETF working group charter where there was, milestones and ideas about what the group would do, sort of specifically. And then what it turned out to have happened is that SDN kind of spread out all over the entire IETF. So as a kind of a constrained discipline, we don't have that, right? So we could induce that, but it's not that way. So basically what we've been doing is running it, as you can see from this, we've been running it sort of like a conference and less like a proto-IETF working group activity. So so as a result, we've been kind of doing this since we started. And the question that Daniel and I were having is sort of like, do we want to do something different? Do we want to try to sort of act as a incubator maybe for IETF working groups in this area? So the idea would be maybe restate the challenges that we have, maybe even rewrite the charter, develop a work plan or some set of work streams if we can. We came up with a few. Let's see, where is it? Okay. Yeah, okay, so here's some of the initiatives or work streams we thought about. So by the way, if anybody has ideas about this, the reason we're talking about this is because I hope people will have opinions on this. So some of the ideas we had were co-locate interim Sdnrg meetings where there are kind of more research-oriented conferences where researchers who wouldn't normally show up here might be there. So here's a list of a few, but there's, just type SDN Space Conference and you'll get the idea. Then the second one here, the incubation program, this was sort of like, the idea here was that we kind of seed work for the IETF, which we're not doing right now. So I think, if you want to know what a different kind of approach to an IRTF working group might be, would be like DTN, right? So DTN had work items in which they were trying to refine DTN down to where they could build an IETF group around it, and now they have. And then the third thing was just more documents in our work stream. So, for example, the one we just heard or others seem like they'd make sense. And so, yeah, so now we really want to hear what people think about what the future direction of the Sdnrg might look like, or what people would like to have happen. Because after all, we're just running it so that one, it'll be productive for the constituents, and two, we might be able to help the IETF in their mission. So not everybody at once, but all the people who want, just line up. By the way, there's a third, while we're waiting here, there's a fourth thing we could do, which is just continue like we are.
So, Carlos Bernardos, I think I like the openness somehow of the research group. So the way of not being so constrained by a charter itself. But I also like the idea of, for some topics that the research group consider that are important, to have a document and work on that, because also that allows us, people bringing things or bringing topics to the research group, to collaborate with other people and to make progress on that research topics. Otherwise it's like a forum where we discuss, but we don't make more progress on those topics. So I think a hybrid approach will be the best for me.
Thank you for that. 1 second, I want to ask you a question. What do you think, like for example, if you have a draft on the talk you gave, where do you think that would cross over into being IETF material? Because that's one of the hard things here, mostly because the breadth of SDN, it covers everything, right? So do you have any thoughts on that?
Yeah, for example, the talk I gave is more an architectural thing. So if we manage to have like an informational document on that architecture then may be reused by other working groups, and maybe think of, okay, this architecture may be used for solving an issue that we have, for example. There are other research groups like work on more on the problems, and then that problem led to a working group, as you mentioned, the DTN, but I mean, multicast mobility was also different. Another example, that there was a document on requirements, and then there was a working group working on that, because at the beginning it was not mature enough to have a working group. So I think there are different cases.
Okay, thank you.
I think it's really interesting in some of these presentations to identify sort of the gaps from the technology perspective. It's with our service model presentation. There's obviously an information model that needs to kind of fill that service requirement, and that's kind of the state that we want to get to. If we want to seed new work in the IETF, we have to have a clear requirement, and we have to identify that actually there is no existing solution right now, not just necessarily within sort of the IETF, but also potentially within other SDOs. And just to follow up sort of the point Carlos made and Dave made, is that there is, with SDN, it's a fairly ubiquitous term, so there's such a wide kind of scope of technology which potentially sits under the SDN umbrella. And one model that Dave and I were looking at was running interim sessions that kind of focused on a very specific slice of that spectrum, And that might sort of be best served by co-locating an Sdnrg with a particular academic conference as well. So that's another model or option.
Anybody else?
Hi, I'm Dirk Kutschner with NEC. So I agree that SDN is like too broad a topic to like go for the DTN approach. I mean, it would be difficult for us. So I thought maybe a good use of the time could be maybe to sponsor some work on finding out what SDN, maybe specific approaches and the concept of probability would actually mean to stuff that is happening in the IETF, so technologies that are currently being developed in the IETF, and provide some guidance, so and like analyze challenges or opportunities. So as an example, so Sdnrg also had a like similar startup situation where we didn't really start up with specifying a concrete protocol or architecture. We kind of got to it over time, so by documenting challenges and finding out what could be a useful angle, and so maybe that could be a way to do next steps here.
Thank you. Dimitri.
Yes, I came in particular because you had this nice talk planned on machine learning, and I think this is...
we could talk about it later.
Well, but I wanted to point at this because I think this is the type of talks we might need to have in order to enter within actually challenges for which we would have to go beyond actually the type of talk that we could have had over the last 4 meetings that we have been discussing. And I remember even 2 years ago we had even more challenging presentations like how do I do in order to get optimization of flows if I have an SDN controller. I remember this presentation by Ed where it was in Orlando, I think. And I think this is probably the type of questions we may ask. You can also steer a research group by asking challenging questions. What if actually we would have more autonomy or more adaptivity required as part of our controllers in order to cope with dynamics in our networks? What if we would like to have a distributed optimization? What if, and I think this is probably another way of dealing with the question that you are asking.
So a series of sort of grand challenges, I think it's definitely worth investigating.
I think that's similar to what Dirk was saying as well.
Mm-hmm.
So this is Raj Jain.
Right.
So I think if we want to do any progress, we really have to have a plan. Because otherwise what we will get is whatever grows and becomes some document. And that would be a list of reads. So I think I'm just going to want to add to what was said a minute ago by Dimitri. What we want to have is a set of challenges, if you can make them, and then put a charter which says that this is what we want to get to, and people somehow get there. Otherwise, like conferences, there will be papers on whatever people are interested in, and I don't know whether we'll really get anything useful.
So, I, understood, and that's kind of the, one of the dimensions of all of this, but I just wanted to mention that when we were starting to do this, Lars took a very, unfortunately Lars isn't here to speak for himself, but he took a very liberal kind of view of what an RG was, right? And one of the things it could be is just a place for people to come and present ideas in a sort of unstructured way, which is what we've been doing. But the reason we're kind of asking these questions is because we want to make sure if there's something else that the group would want to do in terms of direction, or if there's a more productive way to kind of help the IETF that would get to that.
Yeah. So I think 5 meetings, you started in 87, you said, right? I think 5 meetings of just collecting ideas should be probably enough. I mean, I wasn't there in any of the 4 or 5, so I don't know.
Yeah.
But I think at some point you should try to dive to converge it to some important problems.
Thank you.
I'm Frank Fitzek, TU Dresden. I like very much your point where you're saying we have to nail it down to understand what can be the contribution to the IETF, IRTF. I think this is not the only group that has the need to really ask this question to themselves. What I would also like to say is that we are working in one of the groups, in network coding research group, in a similar space where we also now, after showing a lot of research results, now ask ourselves what we want to do with the group. And one thing that we are doing, which is also bridging into the SDN group, is that we try to combine network coding together with SDN, building real products out of that. But we also ask ourselves, what is the next step? Where to put the RFCs there? Where is the contribution to both of these groups? So I think there's one more linkage that you could put on your slides. Thank you.
Thank you.
Into RG.
Anyone else? I guess we're sitting between you and beer.
Yeah. Well, and NFE-RG.
NFE-RG as well, yes. Okay, well, if you haven't signed the blue sheets, please do so, or whoever has them well, there's one up here. So if you haven't signed it, please come up here and sign it, and thank you.
Oh, well,
thank you. Thank you very much. Nobody yelled. Thank you. Really appreciate it.
It's those Macs. They're so unreliable.
Really appreciate it. Hey, sir. Hey, sir. I'm glad to do this.